Hello, I'm Han from SNU, and thanks for the organizer for making this really nice workshop in CVPR, and thanks for the audience for being here in this early morning. I particularly appreciate Michael, so that we can have lots of people in this early morning. Thanks to you. So, right, let me begin my talk with this talk title, Understanding 3D Humans in Contextual 3D Spaces. So let me begin my talk with this example video with the question about why humans move the way we do. I think the first reason is to achieve some physical goals, such as moving something, manipulating something, which we call human-object interaction field in this computer vision era. Um, and maybe the second reason is for basically human-human interaction. So in this case, we use our body motions to transmit some communicative signals. For example, we use some body proximity cue, facial expression cue, hand gesture cue, all these things as a kind of language so that we can convey some intention or emotions and so on. So why global 3D humans? I think the main reason is that if we actually can get the 3D humans in the global location with the environment or other people, we can better understand the human in the scene and the context. In that reason, we actually need to measure both humans and scenes and surrounding environment altogether. So in this talk, I will be conveying our research on this direction in these two particular directions on human-object interaction part and human-human interaction part. And let me maybe begin with this human-human interaction part first with this interesting figure of US former president. I forgot his name, sorry. But anyway, if you see this example, the person is actually using the body proximity for a very interesting way to convince other people. It's quite unusual, right? The kind of close distance between people doing this interpersonal communication is quite unusual, but he used this kind of signal to convince other people. In fact, there exists this interesting theory in psychology called proxemics, which is about a study of the use of the space in interpersonal communication. So based on this idea, we actually have several layers of distance we use in interpersonal communication. For example, we only allow very short nearby distance for our, for example, families, like less than a meter. If someone else is within this boundary, then we feel some uncomfortability, right? And during the social interaction, we usually put the people within like this social range from 1 meter to 4 meter. This idea has been proposed like many, many years ago, 1960s. And in fact, during my PhD time, we really tried to somehow analyze something similar thing with our Panoptic Studio system. This is, I would say, ancient system. The system is gone at CNU, but the system has more than 500 cameras. When one of the major reason of building this system is actually to study the social behaviors of the people. So for that purpose, we designed this social game called haggling, where there are three people playing this game. There exists one buyer, and there are two sellers. And sellers are basically selling a very competitive object to the buyers, for example, iPhone or Galaxy. So the buyer needs to sell the object to the sellers need to sell the object to the buyer. And because of the reason, you can actually see lots of interesting behaviors authentically emerging during this kind of interaction. So using our system, we try to capture their body motion, finger motion, especially the global location, the relative location orientation of the people, face orientation, and body orientation. We do this kind of capture with more than 100 participants, capturing more than 180 haggling gates. And if you see this example from the top view, you can actually see quite interesting social formation during this kind of interaction. So we usually have these kind of triangles, or if you're talking with three people. And if we just simplify the signal and we only think about the essential signal, such as their location and orientation here. So you can only see their location, face orientation, body orientation. There is just some specific pattern here. So one of the interesting direction we tried at the moment here is, can you actually estimate the desired location of the target person by using another two people as the input? So in this example, the red sphere is the ground truth, and the blue cube is our prediction by using either two people's location and orientation as the input. We just use very simple neural network here as a regression problem. And it turns out in this very narrowed down scope of social interaction, we are quite successful in estimating this social formation because there exists some specific pattern during human-human interaction. If we visualize that in a single plot like this, we plot the seller's locations with respect to the normalized bias location. You can actually see the quite interesting average distance between buyer and sellers and within sellers. The range is around like 1.24 meter to 1.51 meter. And that's quite aligned to Edo's Hall's result like 60 years ago, between 1.2 to 2.1. So the main reason why I bring my PhD work here is that I do believe this is really nice time to reinitiate this kind of result, because in our previous scenario, we really need to narrow down the scope, because basically measuring the human's behavior in all kind of scenarios is too challenging. But nowadays, we do have much better tools. For example, this word-grounded HMR, or many nice tool to measure the human behavior from individual images. So I think one interesting direction along this line is if we can measure such kind of lots of diverse human behavior or human-human interactions in the videos and images, can actually use this kind of cue to better understand the human's behavior in more general scenarios. Our lab is also working on this direction as well, but I do believe this is really a new research direction. So if you are interested in, feel free to try this direction. And for the later slide, I would like to also introduce our lab's effort to scale up some motion capture data into two different directions to better understand human behaviors. So the first direction is called mocap every, and in this paper, we try to measure human motion for long-term and outdoor environment using a light-weighted mocap system. So our mocap system is basically a head-mounted camera or egocentric camera and two smartwatches from which we can get IMU signals. So on the right, you can see how easy to wear this system, basically two Apple Watches and one egocentric camera. So we use this egocentric camera video and two IMU signals from Apple Watches as input, and we pursued to get the full body human motions as shown on the right. And this is quite challenging problem because obviously the camera cannot see the own body in most cases, except some finger motions. So the input is extremely sparse. So our input is video and IMU signals. So briefly, in our pipeline, we first estimate the SLAM output so that we can get the world coordinate and the point cloud, that basically the scene and the cameras registered at each time frame in this world coordinate. And we basically use these sparse signals, the cameras, which is basically telling the location of the head at each time, and IMU signals, so that we can get this kind of estimated full body motion. I'm not going to get into all these details, but the core kind of point here we want to measure is basically the height of the person, because to measure the height of the people, we need to also measure the flow level in every frame. So from the ground to from the point cloud reconstructed from the SLAM, first we measure the ground level regularly, and then we can basically get the height information by considering the camera location and the flow location here. And to this end, we basically use all these signals of human height and the human head pose and IMU signals so that we can estimate this kind of final output here. So on the left, you can see the egocentric view. As you can imagine, the own body is not visible from egocentric view. Nonetheless, our estimation for the full body is quite successful, as shown on the right. And more interesting thing is basically this one. If multiple people are wearing the similar devices, basically we can position them in the same world coordinate, because if they are sharing the same global coordinate system and the global point cloud, we can basically register their cameras in the same 3D coordinate. With that, we can have this kind of output here so that we can measure their multi-people interaction in the same coordinate system. So our kind of future direction is to use this kind of system so that we can collect more long-term in the wild motion captures so that we can scale up the data. And a bit orthogonal direction is to focus on human-object interaction, which we call para-home system. And the system is actually presented in this CVPR. Feel free to visit our poster session on June 13th. So this is a basic teaser of our system where you can see basically the very usual kind of human-object interaction, like kitchen scenario, where we can have human body motion and human finger motions, and also object all this movement in a parametric space. So this is another example here. You can see finger motion, body motion, and everything. So we call this system as para-home so that because we try to actually put entire scene into a simple parametric space that is basically this SMPL human body space and also the object space, basically 60 object location and translation, and also some articulated model motions for each object. We also annotated the text prompt for each sequence so that we can also study more interesting stuff like text-to-motion prediction. So to this end, our system pursued to make a very natural room setting, and we try to capture both body motion and finger motion. We try to put multiple objects, and we try to consider more kind of natural scenarios so that human can behave in a sequential kind of manner with multiple objects at the same time. We have collected about more than 400 minutes of data. This is the the view of our system. You can see lots of LED cameras, lots of markers, and we basically use the IMU-based motion capture suite because we want to be more robust to the occlusion during this HOI scenarios. You can see lots of occlusion scenarios. And in fact, we use markers because the raw pixel data is not our main focus. Our main focus is to obtain more accurate human-object interaction. We also try to 3D scan entire object like this. And if the object have some articulated motion, we try to also build this kind of articulated model for each object so that we can express each object movement with just 60, orientation 3D translation parameters with this articulated motion parameters. We can also very naturally estimate the pseudo contact map here. It's not super accurate though, but we can just measure the distance between the object and the human. More other example here. So you can see opening the closet, putting the object on the oven, and so on. Manipulating the button. So yeah, every object and buttons are modeled in an articulated model. And with the same setting, we asked many people to perform the same scenario. But as you can see, the people's motions are quite different each other with the same scenario. That's one interesting point of our data set. Turn on the gas stove, you can see many different style of the motion. So entire motion data set is already available in the internet, so feel free to take a look at those. So one interesting direction of leveraging our data set is to basically synthesize some desired human motion given the object movement. For example, if we want to build the opening of the fridge motion by using this object state transition as the input, we can build basically the motion synthesis model so that we can synthesize this kind of human behavior paired with this input data. So these are some examples of the input. So given the input, we can build a model to synthesize this kind of desired human motions. Okay, so I just have introduced our lab's effort to scale up the motion capture data because this kind of human object interaction motion capture data is quite useful and important for our next future directions. However, the holy grail of this direction is indeed to capture the human-object interaction from in the wild images and videos. However, this is extremely challenging. So let me also introduce our lab's effort in such direction, which we call DAVID, Modeling Dynamic Affordance of 3D Object using Pre-trained Video Diffusion Model. So the idea of David is quite interesting. So we just consider any target object, let's say a cart. At first, we can basically synthesize the images where the person is using the specific target objects, for example, like this image. So these are the synthetic images generated in this flux model. More interestingly, we can also build this video diffusion model output so that we can now even know the dynamics of human-object interaction. For example, in the static image, we know where to grasp it when we are using this cart. And in this video, we know how to use this object temporarily. For example, we need to push the cart rather than lifting them up, right? So if we can somehow leverage this kind of video diffusion model, we can hopefully get the 3D dynamic affordance information as well. So you may ask the question like, why learning 3D HY from synthetic images rather than, for example, real images or real videos? So let me share our thought along the question with this example here. So this is a search result with the prompt like riding a bike. If you actually search some specific HY scenario in the internet, the output is extremely noisy. You often have many people in the scene, cluttered kind of scenarios, lots of occlusions, cropped images, maybe some images only focus on the face or bike itself rather than the entire human and object. And also, you can often see some biased viewpoint, usually the side view or in the front view and so on. Compared to that, if we use the pre-trained diffusion model for synthesized images, we can have much better controllability. Of course, the image quality may not be photorealistic yet, but that would be more than sufficient to learn the human-object interaction, for example. And you can actually enforce the output to have only single person, entire body within a single frame. And more importantly, you can also diversify your viewpoint by using additional prompt, for example, frontal view, side view, and so on. This is the output we've got like 2 years ago using stable diffusion model. And more recently, the more recent diffusion model generate more photorealistic output. So all these things are synthetically generated one by controlling the viewpoint using prompt. The cool thing of this direction is basically you can apply the similar idea for any object. So a bike, a surfboard, basically any object can be synthesized with this kind of model. So with this idea, our lab has been tried to make several kind of directions. So the first paper course is about 3D spatial layout from synthetic images. The second one is more about comprehensive affordance. And the David is about dynamic affordance, which I will present now. So let's just assume that we are given a single target object in 3D, a reference mesh model. Using this video diffusion model, we can generate lots of diverse HY scenarios, and we do some uplifting from these 2D videos so that we can get 4D HY samples. Of course, generating such sample is so challenging thing, so we will just share our pipeline here. And once we have lots of 4D HY samples, we can basically fuse those information into a single motion diffusion model. So here, we can actually build a motion diffusion model specific to each human-object interaction so that we can sample some diverse interesting HY motions. So more specifically, let's assume that we are given this a target 3D object. We choose a viewpoint and we render the 3D into the view. Then we extract the canyon edge so that we can use this as the input for the control net. Using control net with flux model, we can get this kind of synthesized 2D HY image where we have people or the person and the background together. And then we use image to video diffusion model so that we can have this kind of video output from which we can basically get some dynamic affordance. And given this 2D generated video, our next goal is to uplift that into 4D sample. Again, this is a challenging direction, so we will share our current pipeline here. In the very initial version, we have some depth ambiguity for the object. The object is smaller, and we don't have the right alignment, and we have additional treatment to get the better alignment. So how do we do that? So given a 2D video, first, we basically use this world-grounded HMR so that we can have human body pose and the camera location in the same world coordinate. For the object, we do not have such thing, unfortunately, so we have another way to get the relative the location and orientation between object and the camera. So first, since we chose the camera location at the very beginning, we already knew the relative location of object and camera. And along the time, we can actually track the 2D, the point, some sampled point from the 2D images, so that we can basically have the correspondence between 2D and the 3D point. And if we have the correspondence between 2D and 3D, that is basically the input of the classical PMP algorithm, from which we can get the relative location and translation at every time frame. So now we have relative location and translation between human and camera and between object and camera, but these camera actually are the same camera. So we can align them into the same global space so that we can have camera, object, and human in the same space. The only problem is there exists this scale ambiguity for the object because you may have big object in the further distance or small object in the close distance. To resolve this depth ambiguity, we simply use this estimated metric depth using off-the-shelf method so that we can actually get the optimal depths which satisfy our depth Q here. So it's just 1 degree of freedom of uncertainty along the array direction. Let me actually show the example with another card because the previous one, the human was just standing. I would say this is more interesting. So on the left side, we do have the synthesized 2D HY video from which we can get the world-grounded HMR output so that we can get the 3D human and cameras together. And using PMP, we can have the relative pose between object and the card. And we merge them together in the same space. And we resolve the depth ambiguity to the right alignment. So these are some examples of this 4D sampling. Of course, there are lots of failures happening here, but the good thing here is every pipeline is automatic from synthetic image generation to 4D samples. So you can just try many, many times so that you can get sufficient amount of output with some efficient sampling algorithm. This is another example of guitar. Cart example, and scooter. Basically, you can apply any object if you want using this pipeline. So once we have this 4D sample, the later pipeline is just merge them together into a single motion diffusion model so that we can sample HY motions from diffusion model. For that, we leverage the predefined motion diffusion model because our data set itself is not sufficient to train the motion diffusion model from scratch. So motion diffusion model already has lots of interesting human motions, but it doesn't have a sufficient amount of HY motions. So we have an idea of LoRa module so that we can fine-tune the MDM model with LoRa. And each LoRa is specific for each HY motion. So if you just replace the LoRa, you can actually sample different HY style. But that is only about the human motion. Additionally, we need to also sample the object. For that, we use this score-based diffusion model. Let me just skip the detail here, but directly jump to the result here. So given a prompt, our final model can sample human motion and corresponding object to location here. So a person walk or a person jump. So there's no jumping or walking in our original 4D sample, but those are basically originated from MDM model, pre-trained model. And we can add the HY example here. And we can also make this kind of very interesting example of person crawls or suitcase example or umbrella example. This HY specific pattern is from our data, and the general kind of human motion is from MDM. More interesting thing here is we can also fuse 2 different LoRa module into a single sampler here so that we can actually have this multi-object HY motion output as shown on the right. All right, so I try to convey our lab's effort in human-object interaction side and human-human interaction side. These are the references of the paper I presented today. And as you'll know, all this work is done by our collaborators rather than myself. And with that, I thank the audience for their attention. Thanks a lot.